Welcome to today's Explainer. We're jumping right into a fascinating mystery at the absolute cutting edge of digital healthcare. Right now, there is massive hype around artificial intelligence in medicine. We read headlines literally every day about algorithms diagnosing diseases with superhuman accuracy, analyzing heart scans and ECGs in fractions of a second. But, well, there's a catch, and it's a really big one. When we take these seemingly flawless, state-of-the-art AI models out of the hospital and deploy them in the real world, into everyday living rooms, they suddenly stumble. So why does a medical algorithm that works perfectly in the clinic suddenly lose its edge when it visits you at home? That is exactly what we're going to unravel today.
Okay, let's dive into this with Section 1, the medical AI hype, expectation versus reality. The tension between our expectations of medical AI and its actual reality outside the clinic is honestly one of the most critical challenges in modern medicine. We kind of just assume that a smart piece of software is universally smart, right? Like, if it can spot a sick heart on a hospital bed, it can surely spot one at your local pharmacy or in a patient's living room. But biology and data just don't work like that. Think about a hospital environment. It's highly controlled, geared towards severe disease. Patients there are usually experiencing active symptoms, they've been referred by doctors, and their conditions are advanced. Now compare that to a community environment, like your everyday home. The prevalence of disease is so much lower, and the people who do have a condition often have incredibly mild, completely asymptomatic versions of it. You are basically comparing a concentrated pool of severe illness to a vast ocean of general health. Which brings us to Section 2, the transportability problem, lost in translation. So what actually happens when algorithms switch locations? They effectively get lost in translation. Moving an AI from a hospital to a community setting isn't just a simple change of scenery. It's a fundamental shift in the biological and statistical data the AI has to process. And that shift is defined perfectly by this term, the disease spectrum effect. Basically, this is the phenomenon where differences in disease prevalence, meaning how common a disease is, and severity between populations completely alter a diagnostic model's real-world accuracy. In plain English, the mix of sick and healthy people changes completely depending on where you test them, and that fundamentally rewrites the shape of the data the AI is looking at. Now, what's really interesting is how researchers tested this, which we'll cover in Section 3, the Preview Valve study, the ultimate AI stress test. Researchers didn't just theorize about this transportability problem. They ran the ultimate AI stress test through a massive epidemiological study called Preview Valve. They wanted to see exactly what happens when an algorithm steps out of its comfort zone. The setup was brilliant. They took a well-established, multitask, deep learning model called the Echo Next AI, which was trained entirely in hospitals to detect structural heart disease. Then they deployed it on roughly 3,000 everyday community-dwelling adults between the ages of 65 and 85. These were not hospital patients. They were recruited from regular retail pharmacies like CVS and Walgreens. The researchers literally went into these participants' homes to perform ECGs and echocardiograms. They essentially brought the hospital right into the living room to see if the hospital AI could keep up. Let's see what they found in Section 4, Hospital vs. Community Reality, the Data Divide. So the crucial point is really in the actual data. When researchers compared the AI's performance on this at-home group to its performance in a hospital group, the differences were absolutely massive. In the hospital population, structural heart disease was highly prevalent. About 43% of the patients had it, and the primary phenotype or type of disease was severe, things like severe heart failure. But in the community population from the Preview Valve study, the disease prevalence absolutely plummeted to just 8%, and the type of disease shifted completely. Instead of severe heart failure, the most common issue was moderate tricuspid regurgitation, which is a much milder, often asymptomatic leaky valve. Hospital patients are vastly sicker, with incredibly obvious diseases. Community patients are mostly healthy, with only a few subtle issues mixed in. And the consequence of that shift is huge. The AI's accuracy is measured by a metric called AUROC, which essentially grades how well the model can discriminate between someone who is sick and someone who is healthy. Well, that score dropped sharply. In the hospital, the AI scored a highly confident 0.83, but in the community, it fell all the way to 0.71. The model completely lost its confidence when it was taken out of its comfort zone. It just really struggled to separate the healthy from the sick. This leads us right into Section 5. Why did the AI struggle? Solving the mystery. The data now demands we answer a central question. Why exactly did the AI struggle so much? I want to pose this directly to you to challenge our basic assumptions about machine learning. Did the algorithm break?
Did the code degrade when it left the hospital server? Did the AI suddenly just get worse at its job? The definitive answer is no. The technology didn't break at all. The disease just got harder to see. The biological signals became incredibly faint. The AI was still doing exactly what it was trained to do, but the target it was looking for had essentially camouflaged itself.
And this brilliantly illustrates the overarching concept. The shift in environment fundamentally changes the game. In a hospital setting, you have high prevalence and severity, creating a clear separation between sick and healthy. But the lower prevalence and severity of the home setting completely alters the landscape. The AI model itself, the EchoNext deep learning model, hasn't changed a bit, but the data feeding into it has completely transformed. To put that into perspective, let's think about exactly what the AI was seeing in those community density graphs. Imagine a data line representing people with absolutely no structural heart disease, and another line representing people with mild disease. In the community setting, those two lines overlap almost entirely. The AI is giving healthy people and mildly sick people virtually the exact same scores. Because community disease is so mild, the electrical signals of a slightly leaky valve look almost exactly like the healthy background noise of a normal aging heart. To the AI, mild disease and perfect health are virtually identical. Let's move to our final segment, Section 6, the future of AI screening, what this means for you. Understanding why this model stumbled completely changes how we should think about rolling out AI screening tools to the general public. The researchers summed it up perfectly, noting that their findings demonstrate the impact of changes in disease prevalence, case mix, and spectrum on AI model transportability across different healthcare settings. Basically, you simply cannot assume an AI works everywhere just because it works somewhere. A hospital is definitely not a living room, and an algorithm trained on the very sick is not automatically qualified to screen the mostly healthy.
So here are the core lessons you should take away from this explainer. First, we absolutely must evaluate AI models in their intended use populations. If you want to screen people at a pharmacy, you have to test the AI at the pharmacy. Second, and this is absolutely crucial, just throwing more data at the AI or retraining the algorithm might not magically fix the issue. If the biological signals of early mild disease are genuinely too weak and buried in normal human variation, no amount of computing power is going to separate them. Finally, true generalization requires intense validation far beyond the hospital walls. I want to leave you with a provocative question to rethink the current AI hype. Is mass AI screening in our communities actually worth the financial cost, the false alarms, and the patient anxiety if it's primarily only catching mild, non-actionable cases that look just like healthy background noise? As we rush to bring hospital tech into our homes, we have to ask ourselves not just if the AI can see a pattern, but if that pattern actually matters. Thanks for joining me for this explainer, and keep questioning the data.